of my career in Microsoft software development and architecture ecosystem, and in the last few years I have also ventured into open source Java, containers, and of course the cloud. Today we'll talk about service meshes. We'll talk about them in general and about AWS App Mesh in particular. Right, so knowing that 42 is the answer, the mesh is the answer, we need to spend a little bit of time to understand what question it answers. And I promise you it will not take us 7.5 million years to find the question. So let's take a look at the recent past, please. I want to tell you a bit of a personal journey story. For that, let me time travel back to 2005 when iPod was the hottest gadget in the world, when a little-known video sharing service called YouTube was launched, and when SOAP web services were proudly ruling the world, unaware of the two impeding mass extinction events known as the ESB tsunami and the advent of REST. At the time, I was working on a product that, in retrospect, turned to be quite ahead of its time. And so here's the background of that product that I was working on. A major credit card company that issues and handles lots of store-branded gift cards decided to innovate by doing something unusual for the time, exposing the gift card payment interface as an internet SOAP web service to simplify retailers' integration job. It was a popular move as retailers would just get the WSDL file and generate service client classes like Java, C#, etc. to call the service. The problem was, if you remember, WSDL was not only carrying API definition in itself, but also the service endpoint information, which usually meant that internal IP address of the developer system where the WSDL file was generated and not where it was running in production. There were more issues on top of the problem with discovering where the service ran. Other problems service developers faced were, how do we ensure that the client is allowed to call us and they are who they say they are? So the authentication problem. Should we tell the person who called our support what our production service IP address is? Where do we even start with managing our client's ability to invoke our service or deny them access if they leave the platform? Do we write code for that? What do we do? If client call us and tell that our service is slow and below our SLA, how do we investigate and prove we were within the SLA, for example? Our InfoSec said they needed to audit clients to know they treated their internal networks as zero trust. Specifically, the card number in the service request would only travel in an encrypted manner. So all these questions, and by the way, how do we spare our developers and hopefully ops from all of these burdens? So retailers who are service clients wanted an easy way to know how to call the service, but they still needed a way to get the IP address of the service through some process, which hopefully is better than just calling somebody with a phone number on the website of the service provider. They had much better thing to do than to prove to the credit card company that their network and practice were PCI compliant, for example. And although they dealt with a major credit card company, retailers' own InfoSec people needed an insurance from the bank that the entire call chain was secure. Well, so much for SOA that was supposed to be easy, I guess, right? Now, those were typical problems for SOAP service era, and at the same time, I was kind of developing my career working for a company at the center of the service-oriented architecture SOA craze, and the product I co-architected was meant to solve most of these issues that I described. Here, what this product did. The credit card company had their SOAP services deployed in a high availability cluster inside their own DMZ. The client ran their client software on point of sale devices or store services. And there was a a cloud of the dangerous internet between those two. Our solution was to deploy SOA proxy we built at the edges of both service providers and retailers networks, and to have another mediating component we called SOA portal. SOA, by the way, again, it's a reminder for those who are very young that SOA stands for service-oriented architecture. The flow goes like this. Both service and provider started with registering their SOA proxies with the SOA portal so that the portal would know who they are. This results in each SOA proxy getting a certificate signed by the portal. Then service provider, SP, can register or publish their service in the secure portal, telling our SOA system that the address of the, providing the address of the service description, and upload its WSDL. So it could specify other service metadata as well. The service provider then registered the retailer as an onboarded client for the service. That results in the following. One, service provider proxy gets the public key of the client cert, so it could verify requests coming from the client. And two, client developers receive the WSDL for the service with the service address pointing to the local SOA proxy on the left. And finally, three, the client proxy getting the internet address of the service provider proxy. So that was all there. And basically, this is all there is to publishing a service and onboarding a client. So this system was very well received for the test that we ran. At the runtime, after provisioning was completed, we ended up with the following. We had built a logical network. You see that orange box. So why is it logical network and what's in it? So we had a logical network where both the client and service proxies knew each other identities due to X509 cert distributed to both sides, where client developers received a WSDL that was always pointing to the local internal network address of the client SOA proxy on the left. And the client called the local proxy via SSL, solving the first mile encryption problem, making their network zero trust. Where service provider didn't need to care about authenticating and authorizing clients in their service code, where traffic between proxies was encrypted by proxies using SSL and requests were signed by the client proxy certs, where performance data and errors information were streamed back to the portal so both clients and service providers could see what was going on, ensuring superior visibility and troubleshooting agility. And by the way, when service provider deployed another version of the service at the address on the right ending at 0.12 instead of 0.11, all they needed to do is to change service registration in the portal, and within seconds, their local SOA proxy would be calling the new version of the service with zero downtime and no changes to the client. Most actions performed by various actors in this system were done through the SOA portal website and resulted in SOA proxy configuration changes distributed to and acted upon by relevant proxies. There is only one significant flaw here I see on this picture. All those SOA components were not given stark buzzwordy names, and here's what I wish I thought of calling those things instead. I wish I called a logical network something different. I wish it should have been named service mesh. The SOA proxy was also close to be called Envoy proxy, but no luck there. The mutual SSL tunnel name could have been simplified to just MTLS, and the SOA portal would feel so much better about itself if we were savvy enough to call it the control plane. Switching to a new service version would sound 1,000 times cooler had we thought of calling it traffic shifting. All right, so many years ago in 2019, I learned that almost 15 years ago, I was smart enough to come up with a service mesh concept independently from what has later been implemented by Envoy / Lyft Istio, and later AWS App Mesh. But I also learned that both then and now, I'm nowhere near being clever enough to sell my wares. And just to be very clear, though, I have not written the Envoy proxy, okay? That was done by the good people of Lyft recently. Now, on this diagram, so this diagram has some notable difference from current crop of service meshes. Modern service meshes typically do not span the open internet and are not necessarily involved in authorizing outside callers. Still, clients can be internal clients just as well for everyone to appreciate how tremendously helpful a system like this is, where traffic can be directed and shifted using control plane, where service call latency and success metadata can be collected, monitored, and reported on from a convenient location. That is what service mesh is in a nutshell. One, it's decoupling a service from a client through simplified managed virtual networking. And two, it's a service topology and performance observability tool at your fingertips. Previous slides present a view of the app mesh mostly from the networking engineer and operations engineer vantage point. Here's a software developer angle for understanding value proposition of service meshes. It's aspect-oriented programming. For those of you here who are seasoned developers, you are likely familiar with the concept of aspect-oriented programming, where so-called cross-cutting concerns are implemented not in the business logic code, but rather are taken outside of it and implemented and injected as side advices. So here I'll spend a little bit, for those of you who are not maybe fully familiar with the notion of cross-cutting concerns and how AOP helps here, let me give you a quick run through here. And I will use a quick story of kind of day in life, or I don't know, a quarter in life of a business logic programmer. So let's imagine you write business logic classes and methods typically consisting of a handful of data access operations. You deploy the backend service app where your business logic is implemented and all is good for a while. Then once in a while, some of the business logic service calls start to occasionally show high latency. What is the cause of it? What is your, was it your logic? Was it caused by a network glitch, a dependency library, database? You now have to instrument your business logic code. You surround it by a couple of logging calls, so you could surface any errors your business logic may throw. You may add calculating the time spent between the top and the bottom of your method for a good measure. And for a while, the situation improved. Then one day, your order placing business logic method lost data because database was briefly unavailable. So you had to add retry logic to avoid losing data in the future. The very next day, the database started getting intermittently unavailable again at peak demand time, and your retry logic from yesterday ended up flooding crippled database because database was running out of connections. And your retry logic tripled the connection demand, so the database could not get back to stability under onslaught of your retry requests. Operations engineer had to shut down your app to reanimate the database, spending hours to recover the cascading failure. That day, you were asked to visit the company CTO office for the first time and not to discuss any raises, promotions. The CTO tells you to implement circuit breakers and exponential back-off retry logic. You Google it and you see that it's not that easy to implement by yourself. You go back to the drawing boards, review your code, and notice that after all the recent changes, every business logic method has only small piece of actual business logic, and instead is wrapped in many layers of instrumentation code. So you smarten up and start using aspect-oriented frameworks, which allow you to strip all the instrumentation code out of your business logic itself and put it in a aspect-oriented advices living someplace else. You use this, you implement the circuit breakers and supplied by AOP framework. Your code is now very clean. Your business logic code is very clean, very lean, and works really well for about a year. So you do get the promotion and the raise for graceful recovery from the tough challenge. In fact, thanks to you, the company gets so successful, it goes onto the acquisition spree and buys a few more products and gives you the task to integrate with these new acquired systems with your product and with all those products written in different languages, all without AOP, some missing instrumentation code, meaning your nightmare that you just recovered from came right back and with vengeance. So you get very depressed and you lift, to lift your spirit, you call your trusted AWS solutions architect and ask her, how can I go on like this? You tell her, if only was a way that aspect-oriented interceptor wrapped not around my business logic method, but rather around my entire web API operation. What if the interceptor lived out of process altogether and could do most of what my aspect-oriented instrumentation code did while not being dependent on a specific programming language or a library? And the SA, this solution architect probably says, I'm glad you asked. The answer, of course, is AWS App Mesh, because it takes care of most of these unpleasant things in the liabilities column here on this slide, regardless of which programming language is used for your web APIs. So for developers, I would like you to think of service meshes in general as an out-of-process AOP framework, where your advice logic, where your cross-cutting concern implementation logic lives outside of your, not just outside of your business logic, but it lives totally outside of your application. All right, so going back for a moment to our year 2005 in review, one of the reasons SOA has been largely abandoned around that time frame had to do with how difficult it was to troubleshoot problems of interconnected services at scale. Enterprises routinely ran hundreds of web services calling other web services, and when an HTTP 500 error rears its ugly head, good luck finding out where it originated and what caused it. If you could think about it, today's microservices are very much prone to the very same problem. Fortunately, we got much better tools these days. We also got much better patterns and practices compared to what we had 15 years ago. First, our processes have improved dramatically. DevOps, CI/CD pipelines are no longer an exception implemented only by the most sophisticated shops. Most everyone has those now. Same goes for unit and integration testing. But we also have a much better, a more consistent application deployment package these days. It's called container. To deploy and manage containers at scale, we've got container orchestrators like Amazon Elastic Container Service, ECS, like Kubernetes, which is open source, which you also can easily run on AWS. One of the critical but somewhat underappreciated features container orchestrators give us is an ability to deploy multiple containers at a single unit. In ECS, it's a multi-container task, and in Kubernetes, it's multi-container pods. That in turn let us build multi-container units where one container intercepts all network traffic going in and out of the multi-container unit, does some processing of that traffic, then hands it over to the main application container. That's one of the main tricks that service meshes do. They attach those sidecar containers to main application containers without requiring any changes to the application logic. Service mesh sidecar containers interrogate and manage network traffic before it enters your application container and then when it leaves it. These service sidecar containers make up the data plane of a service mesh. Configuring sidecar containers is something done by the service mesh control plane. We'll talk about it a little in a little bit more detail as we go along. just looking at this slide, I would like to kind of plant it in your minds that microservices plus containers means that you very likely need service mesh. For running a monolith, for example, in a container, service mesh is desirable, but because service mesh has its own complexity, learning service mesh to run one or two large monolith may be not necessarily the best trade-off between the complexity. You might be trading one complexity for another. But if you're running microservices in containers, service mesh is pretty much guaranteed to add quite a bit of value. So I want you to kind of, if you decide that all these tales I tell today, they are pointless, just make a mental screenshot of this slide. So microservices plus containers equals service mesh. Now, let me reframe a little bit the context around the motivation for building a solutions like service mesh. Over the last decade, several patterns have emerged in how software is built and deployed. Containers, again, are a great way to package, deploy, and manage applications, especially those built using a microservices architecture. There are many benefits in using containers, from packaging and dependency management, maintaining consistency through various stages of development, testing coherence, but the crucial one is the ease of scaling. The scale, though, can become difficult to manage, and it introduces new problems. And sorry for brief interruption, got distracted. So what kind of problems the ease of scales create? This is a group of problems that are sometimes colloquially known as day two problems. Going back to the problems of our business logic programmer, you may remember that all problems they encountered were discovered after the application was deployed. Now, just like back then, getting a few services up and running in containers, just the same as it was during the service architecture days, is a start. But when that grows to hundreds of microservices deployed in thousands of containers, following issues arise. What exactly is happening in your cluster, and how are your services interacting with each other and performing against baseline expectations? Where do errors originate? How do you manage and monitor traffic between thousands of abstract compute environments? Are there standardized ways of automating policy and creating a secure by default environment for multiple development teams? Ultimately, what can be done within the infrastructure to improve overall experience of your customers? We can further categorize these day two requirements as follows. First is in this category is first category is observability. This is a topic unto itself. The practice of building systems with metrics, traces, and logs, not unique to cloud native applications, as we've discussed, but can be difficult could be difficult and expensive to manage at scale in cloud native environments. Traffic management requires routing and traffic shifting policies to implement granular access controls and to simplify rolling deployment strategies. Security and policy require solutions like end-to-end encryption, certificate management, and policy creation, distribution, and enforcement, which together give sanity to your large-scale deployments. Resilience, required infrastructure feature, which let you configure various behaviors like timeouts, retries, and circuit breakers, decoupled from application source code, just like AOP. Again, all these four things, the observability, traffic management, security, and policy, and resilience, all of them are just categories or classes of cross-cutting concerns. Right. So, and all of these categories of issues of day two problems, they obviously need to be addressed. So a service mesh is like a Swiss Army knife for these types of day two problems. With AWS App Mesh, you can solve these problems and more. There are multiple service mesh implementations. Today, I would like to introduce you to AWS App Mesh. It is a fully managed AWS service, and it delivers on service mesh promises. It makes it easy to monitor and control traffic between your services. It provides consistent visibility and network traffic controls for every service that is part of the mesh. App Mesh supports applications running in containers in Amazon ECS or Amazon EKS using either EC2 or Fargate compute nodes. It also supports self-managed Kubernetes and EC2 instances, virtual machines on AWS, as well as applications deployed on EC2 virtual machine instances with or without containers. But most importantly, a single app mesh can span Amazon accounts, ECS clusters, EKS clusters, and EC2 instances, forming one simple logical network that applications are aware of, hiding away all complexities of heterogeneous compute substrates and networking infrastructure. That enables easy integration of microservices created by different teams with different skill sets and design philosophy into a single logical network. Finally, unlike open source third-party service meshes, AWS App Mesh is well integrated with other AWS services and is fully supported by AWS. Just once again, perhaps some of you are familiar with a popular open source service mesh called Istio. An important thing is that Istio is pretty much bound to Kubernetes. Istio is a service mesh built on top of Kubernetes and limited by Kubernetes. If you don't use Kubernetes, you don't use Istio. AWS App Mesh, while solving the same class of problems, can span multiple container orchestrators and multiple compute technologies like VMs, EC2 like VM, EC2s in AWS parlance, Kubernetes clusters, and ECS clusters. You may have two services deployed. For example, one will be deployed in an ECS cluster and one deployed in Kubernetes, and they still can talk to each other through the simplified means of the App Mesh. AWS App Mesh is available at no cost. You only pay for consumed resources like compute, storage, and networking, some of which are used by App Mesh components. AWS App Mesh provides a control plane that you interact with to express intent for configuration, and a data plane which is deployed alongside your application software, monitoring and managing all the traffic on the wire. But by virtue of its design, AWS App Mesh is in a position to provide features to address all of these needs, all of the needs we discussed so far. There is no magic in the cloud, so let's get into some details as to how App Mesh works in order to explain how it can meet these needs. As you can see from this wall of text, AWS App Mesh has a lot of features. Some of these are exposed from the proxy software used in the data plane, which is Envoy. Envoy is an open source project, one of the first graduated project in CNCF, and has a vibrant community and ecosystem. I'll talk about Envoy a little bit more in detail on the next few slides. Envoy is ideal for its role in the App Mesh, given its very efficient and highly performant nature. Along with Envoy features, App Mesh offers additional features, functionality, and integration with other AWS services. We'll refer to some new features in our roadmap toward the end of the talk, time permitting. Well, I'll be first to say that this overview of AWS App Mesh architecture is a little bit of an eyesore. No doubt App Mesh can be complex to new users. When considering the complexity of a solution, I'd urge you to weigh that complexity of the problems it's designed to solve and against the complexity of the tool. And by the way, the problems that it solves are really hard. That said, it is a goal of this talk to explain these components so that the image not only makes sense at a glance, but that you understand how this architecture implements the features we've discussed. We can see here at the core of the solution, each deployed service has an Envoy proxy instance running alongside it. This implements a data plane. These Envoy instances receive their configuration from the App Mesh control plane based upon the configuration you gave it, and the proxies manage the traffic within the mesh based upon that configuration. You can see integrations with various external solutions, including other AWS services, partner solutions, and solutions you may choose to manage yourself. Okay, let's go a little further down the rabbit hole. Zooming in on a couple of services, we see the relationship between them and the Envoy proxy instance. The proxies are managed and monitored by App Mesh, and in turn, they route traffic as needed. In this manner, all traffic bound for your application services flow through App Mesh data plane and can be managed and observed. In this case, we see that the proxy for services A and B are intercepting traffic and routing to and from them. The proxies could be configured to send a different version of the same service, a different service altogether, or simply drop the traffic if that is necessary. As you saw in my introduction story, a proxy is the key component of the service mesh, and specifically its data plane. A few years ago, Lyft, the ride-sharing company, has open sourced its proxy component named Envoy. Envoy has tons of networking features, and configuring those features and behaviors is quite complex. And this complex configuration is one of the main things that service meshes built around Envoy try to simplify. Another important job of service meshes is to collect, process, and present telemetry, tracing, and other metadata generated by proxies. Envoy is extensible, making it a good candidate for building fully fledged service meshes around it by third parties. Envoy is designed to run as a sidecar container together with your application container, or Envoy can also run as a standalone proxy, as a standalone process if you're not using containers. Sidecar is a little bit of a misnomer here, as Envoy is more like a wrapper for your container. Envoy by default proxies all inbound network traffic coming into your container, as well as outbound traffic sent by the app container downstream. So this picture where you see Envoy proxy sidecar container in red, which is wrapped around your app container. So Envoy is that thing that where our cross-cutting concern advices effectively run from this point on. Next, I'd like to go over the various aspects of App Mesh configuration. This is where some of the complexity creeps in, but it's also your door into using the service. So I'd like to go over each component, and there are not many of them, I promise, and the relationship between those resources before we try to use them in action. App Mesh leverages several abstractions that let us express the configuration for our service mesh for applications within. Whether you're using ECS, AWS Container Service, Kubernetes, another AWS service, or CLI or API, App Mesh constructs are the global API to express your configuration intent to the service. Now, why all mesh resources? You see this slide, right? And you may ask, why all mesh resources are virtual? That's because all these virtual resources is just a convenient abstraction for defining and distributing Envoy proxy configuration on a need-to-know basis. All virtual resources end up configuring one or more Envoy proxy setting. So again, Here on this picture where you see traffic flowing from your application A to application B, and you see Envoy fronting both outbound traffic and inbound traffic. When we try to describe this picture, we will use these components. We will create virtual nodes, services, routers, routes, gateways, and gateway routes. And they are virtual because they don't really exist. Here you see, this is a true picture. You see traffic flowing from A to B through Envoys. And you will see on the next slide that we'll start drawing a lot of boxes here in between. And all those boxes will represent just imaginary structures. Then once configured, simply create configuration settings for this Envoy, and control plane will distribute those configuration settings to this proxy, to these proxies. All right. So I'm kind of jumping a little bit ahead, but let's try to look at how our virtual resources will turn into real network traffic control. So the overarching abstraction in the app mesh is the mesh itself. This is the logical boundary for network traffic between services that reside within it. The service mesh contains all of the other constructs that make up the mesh. Most importantly, this is your boundary for easy service discovery. App mesh may span physical networks and unrelated services like ECS, EKS, and EC2, but for meshed application, that complexity gets replaced with the mesh simplicity. So first is a virtual node. Virtual node acts as a logical pointer to a particular group of containers, such as an Amazon ECS service or a Kubernetes deployment. When you create a virtual node, you must specify a service discovery method for your container group. Any inbound traffic that your virtual node expects is specified as a listener, and any virtual service that a virtual node sends outbound traffic to is specified as a backend. So if your application has inbound traffic, it comes through a listener, and if it goes downstream to another service, it's defined through a backend, and both are the listener and a backend are properties of the virtual node. Let me go back for a second. For those of you who are familiar with Kubernetes, you know how you create a Kubernetes service, and that service has a selector specifying container pods, effectively, and it says, for this group of containers, I will create an HTTP or HTTPS endpoint, right? So in Kubernetes, service represents the group of pods, group of containers. In AWS App Mesh, a virtual node represents the group of containers. And here's an important thing to keep in mind. It's still quite possible that you will be using App Mesh with Kubernetes, with EKS. But you need to remember that unlike Istio, for example, AWS App Mesh is not bound to Kubernetes. AWS App Mesh can work on ECS, where we use different abstractions like tasks and task definitions instead of deployments and services as in Kubernetes. And yet App Mesh needs to work with those different set of abstractions. And that also expands to EC2 as well, because you can just run a container on EC2, and you can run a proxy Envoy right next to another container, or you can even run a process on a virtual machine, and you can run Envoy as a standalone process as well. So all of these permutations are supported by AWS App Mesh. So I just want if you come here with a strong Kubernetes background, you know what Istio is, you used it, you need to kind of unbias yourself against, to fully comprehend the notion that AWS App Mesh is not just a thing inside the Kubernetes, okay? Right, so next virtual resource that App Mesh introduces is the virtual service. Virtual service represent those services provided by virtual nodes and connect your network traffic to them. The relationship between virtual services and virtual nodes and a related configuration is important to the behavior of your application within the mesh. So again, to kind of rely on Kubernetes equivalent, virtual service plus virtual node is roughly what is deployment plus virtual plus the Kubernetes service, what they accomplish together. This is what is done with virtual service and virtual nodes. Next is a virtual router. Virtual routers are optional intermediaries between virtual router and virtual node. Virtual between virtual services and virtual nodes. Virtual routers can route traffic for virtual services and direct the traffic based upon your configuration specification. Here we see virtual services name paths, and it's sending traffic to a virtual router of the same name. Virtual routers then direct traffic downstream towards your virtual nodes by specifying routes. Although virtual routers are optional and virtual services can send traffic directly to virtual nodes, virtual routers are necessary to implement traffic shifting patterns that enable blue-green, canary, and other application deployment strategies. Again, if you're familiar with Kubernetes, perhaps the way you implemented canary and blue-green deployments in the past, you would have a service that fronts pods created by two different deployments. For example, one is a deployment for version 1 of your service, another deployment of the version 2, and your Kubernetes service will have a pod selector that matches both version 1 and version 2. What will happen here is you achieve kind of like blue-green or canary deployment through just purely Kubernetes means. But the problem here with just pure Kubernetes is in order to do traffic shifting, for example, if you want to split traffic 80-20 between the old version and the new version, you would effectively have to launch 4 replicas of your 4 containers with your old version and one container of your new version. So altogether it's 5, and this way you achieve 80-20 split. The problem with that, of course, you may not need to run 5 containers. Maybe that's way over provision your service and you will end up paying for resources that you don't use. So what a virtual router gives you is you don't need to run 5 containers to achieve 80-20 split. Just like with any most of app service meshes, you can just use service mesh construct to achieve 80-20 traffic split between just 2 containers that we see here. All right, next virtual resource is routes. Routes can be HTTP, HTTP2, gRPC, or TCP based. They are specified using match criteria, which can be path based or be driven by headers or by quite a few other things depending on a network protocol. Configuration of these routes is what enables all of the traffic shifting features of the app mesh. You can specify a relative priority for a route, and you can configure multiple virtual node destinations for a given route and weigh the traffic between them. For example, to achieve a quick A/B test between 2 versions of a service, you can easily send 50% of traffic to one version of a service and 50% to another. That can be used to simplify many types of deployments, canaries or blue-green deployments, for example. And some resilience features are configured through routes as well. For example, you can specify a retry policy for a given route and decouple that pattern from your application source code. This can be managed through route configuration across a set of services and changed very easily at scale. Virtual gateways allow you to specify ingress rules for traffic coming into your mesh. While typically we are concerned with east-west traffic within the mesh or traffic between services, virtual gateways provide us with ability to define the path of inbound north-south traffic that originated outside of the mesh. One thing to note is that unlike all other virtual app mesh resources that are truly virtual, one can't configure just a virtual gateway and expect traffic to ingress into the mesh. In addition to having virtual gateway, one has to configure Envoy proxy running at the mesh edge, either as an ECS task or a Kubernetes deployment, along with corresponding services and some other resources. Virtual gateway has has 2 point to containers running Envoy proxy, similar to how virtual nodes front actual application containers running along with Envoy sidecars. Maybe it's a little complicated, so let me try to maybe rephrase this. So virtual gateway is not really virtual. There will be an actual Envoy proxy running here. It has to be. So I personally prefer, instead of calling it virtual gateway, I prefer to call it ingress gateway. And AWS has a component that you can install. For example, if you install it in Kubernetes cluster, you can install it through Helm chart, and that component is called ingress gateway. So among all of this bunch of virtual resources, ingress gateway is not really virtual. It's a real meat and potatoes thing. And to tie this all up together, virtual gateways also use gateway routes to define ingress rules and to specify the flow of traffic from outside the mesh to virtual services, right? So in the end, we'll have this picture. Here we see, let me get a sip of water because I feel like I'm losing my voice. Here we see a slightly more explicit architecture diagram of a simple application running within App Mesh. Hopefully this makes clear the various components of configuration and their relationship. We see traffic ingress through the virtual gateway, and its gateway routes pass the logical flow to the virtual service named paths. From there, paths virtual routers send traffic to one of two virtual nodes, full SVC or bar SVC, based upon the HTTP route prefix matching either full or bar, respectively. Finally, traffic will end up at one of two services, full SVC or bar SVC. Here I need to remind you that although we have quite a few boxes here showing multiple resources, all virtual resources do not actually exist in reality and are just a way to configure Envoy proxies, which in this case live in three places. One on the left, where ingress gateway is, and two others are on the rightmost side, where application containers run. While thin black arrows show logical traffic flow through the mesh, thick orange arrows show actual real-life traffic flow from real ingress gateway to real application ECS task or Kubernetes pods. All virtual things simply get transformed into configuration settings of those three envoys, and those settings get delivered through control plane to envoys. Finally, to define your app mesh resources using infrastructure as code approach, you can use Amazon CloudFormation for ECS and Kubernetes manifest, or better, Helm templates known as charts. There are some additional configuration opportunities within the app mesh, But with what I've covered, hopefully you have a clear idea of various contracts needed for your application to get up and running within App Mesh. So this is pretty much it. Just one more time, I want to reiterate. So in the end, your App Mesh will comprise just 3 groups of containers. One will be just a container with a standalone Envoy proxy, which serves as the ingress gateway, which dispatches the traffic to one of 2 application containers. And these application containers are fronted by the Envoy proxy containers. That's it. So all of these boxes in between, they collapse into the Envoy configuration that gets distributed to these 3 places. And this is what App Mesh control plane does. So I think this is a pretty high cognitive load type of session. So I will wrap it up. I would like to get to the, if we have a little bit of time left, for Q&A. And I will also paste a couple of links in the chat in a second. So first link will be the YouTube video, where I take you through deploying, to doing the entire thing from scratch. This video shows you how to build a Kubernetes cluster on AWS, create an app mesh within that cluster, Kubernetes cluster, deploy required integration components that make Kubernetes cluster work together with AWS App Mesh. Then it shows you how you take your take 2 applications, 2 containerized applications, how you deploy them to EKS Kubernetes cluster to namespaces that are mesh enabled. So this entire thing, it's quite a lot, quite a bit. It takes about an hour to go from A to Z. But I also, in that video, I have, if you go into the YouTube description of that video, you will see that each step has a shortcut in the description. If you click that expand in the description of YouTube video, you will see shortcuts to specific segments. And if you, for example, know how to deploy Kubernetes cluster on AWS, you don't have to watch it. You just skip somewhere just to the middle and take full advantage of that. And of course, I would like you to let me know whether what I've told you today was useful. Was it too little, too much, just right? And once again, I want to thank you and to remind you that the App Mesh is something that you're likely to really need if you are going to run microservices in containers. There are other options to run microservices. For example, in AWS, you can run them as serverless Lambda functions. But if your target is containers, if you are going towards microservices, you probably will be well served if you attend another session like this, if you read up about AWS App Mesh, if you watch that video, you're likely going to make your life much, much easier. All right, so I will stop the presentation at this point, and I'll take a second to copy and paste these links into the chat window. Thank you, and we can switch to Q&A if you have any questions.
Yes, very nice. Thank you, Vlad. Does anybody have any questions on anything discussed?
So the first question I see is whether I will be able to post the slides. Yes, I will email the slides to Mark if that will work. And we'll after, okay.
Yeah, I can
Right,
post
so
it
let me go ahead and give you these links in the chat window, please. All right, so those are the videos, the feedback that I would really appreciate if you gave me, and my email address should you have any questions. And if you have questions about App Mesh, if you have in-depth questions, I will be able to put you in contact with AWS people who are specializing in App Mesh. And I would also like you to keep in mind that your company may benefit quite a bit if your company becomes AWS partner. And with that, if you have any questions, please post them, and or just turn on your mic and video and ask them, please. Or if not, Mark, it's all yours.
Okay. Any
So
questions?
just says what the pricing model is.
All right. So App Mesh comes at no additional cost for the App Mesh itself, but you will be using some resources, AWS resources like compute. For example, you may run EC2 instances. You may use some storage. You will use some networking. So those resources do cost money, but App Mesh itself does not. But please keep in mind that you will be running additional components like Envoy in your data plane. Envoy will consume some of those compute, storage, and networking resources, which means that it will add some amount of money to your bill. But App Mesh itself, just like EKS, for example, Kubernetes on AWS, by itself, it does not cost anything. Again, it's just those fundamental resources consumed through that. And by the way, for example, if you were to roll out your own Kubernetes cluster or your own, say, Istio service mesh, you would have to deploy not only data plane, but also control plane on those cluster nodes. That would be more cost, because what happens with AWS for both Kubernetes and App Mesh, we do run control plane on our own resources, and we don't charge you for that. You just run the data plane, your own workloads, you run the Envoy proxies, and that's pretty much all it adds. So that's a pricing model. There is another question. Do you have some idea how widely App Mesh services are being deployed, and some idea of ROI via agility or just migrations from legacy to new way of doing things? So in all likelihood, App Mesh is not going to be your migration destination. More likely is going to be your modernization destination. If you just forklift, do the lift and shift of your workloads, your application from on-premise to the cloud, to AWS in this case, you are not likely to put it in the App Mesh, I think. So that is not what I think is the lift and shift migration scenario. But for example, if you take a monolith application and you say apply strangler pattern to start taking out smaller pieces as your microservices, as you start putting them, say, if you containerize them, first of all, you containerize them and you put them either on AWS ECS, you put them on Kubernetes, run them as such, then at some point you will go through all those pains that I described in the very beginning. It's like all of a sudden some service is slow. How do I find out what's going on? And I want to do it kind of at a click of a mouse. And by the way, you've seen all the slides today, but if you watch my video, you will see in practice what it looks like. You will see the application that gets deployed to EKS. You will see AWS X-ray that shows you the graphical representation of the traffic, how it flows from outside, from the edge of your App Mesh cluster, App Mesh, to your ingress gateway, then it flows to your client, and then it flows to your service, and you will see it graphically. You will be able to click on that and like click on a connection between, say, the client and the service, and you will see trace information telling you how much time it took. So that is how much more you get from the App Mesh. Again, the idea of ROI, I think I probably won't be able to give you a dollar number here, but think about it this way. If you were drowning in that cross-cutting concern implementation, imagine if you're a programmer, I hope, not hope, but I think that quite a few of you are. You're writing a business logic where you say, okay, this typical transaction, take money from account A, put in account B. You write it like you do the transaction, you do a couple of business data access calls to your database, you call it a day, and then all these other operations time, day two problems start to crop up, and you start racking your mind, how do you do it? And then the complexity that you introduce, that complexity in turns adds liabilities, like we discussed, when all of a sudden the retries that you were so proud to implement all of a sudden breaks the production because your database cannot cope with DDoSing that your retries created. So all of these day two problems, they are real. But maybe as developers, we don't have to deal with those. It goes on the shoulders of operations people. But here, what we say is, if you understand the value proposition of implementing cross-cutting concerns in aspect-oriented framework, you are likely to understand the value proposition of App Mesh. So in the long run, when you run your microservices at scale, it's very, very likely is going to make your life much easier, even at the expense of you having to go through the learning curve and learning all of these 5 or so virtual resources and how to configure them.
Very nice. Any other questions out there? So I actually
do you have an example of a monolith that was re-architected, whatever the journey and milestones were like? And by the way, thank you for the kind word here. Condensed. Yeah, it's if condensed but highly informative. By the way, if you attend my other session at the end of April, I think 20-something of April, on Kubernetes, it's also going to be pretty condensed. And the reason I do it this way is because these are really complex topics, and I personally spend quite a bit of time learning them, going through them, and because they are so new and then they grow so fast, the documentation is not quite there. And a lot of what we get as resources, the YouTube videos, the blog posts, all that, they tend to be hello world. How do you start? So I want to go a little bit deeper, and I want to share things that I wish I grasped from the beginning. For example, the part that virtual things are not real. It's like in the Matrix movie, there is no spoon, right? So stuff like that. So regarding the monolith, I may try to find the customer reference, the public customer reference for strangling the monolith into microservices. But I think Eric Stroll has the wonderful example, and it's quite old, of how to do that. I know my coworker, my colleague, has gone through the exercise of strangling the monolith into microservices, and it was successful. So just look up strangler pattern, and you will find a lot of resources that are valid. And I just want to assure you that, yes, we do have real world examples of that being done. It is a journey, though. And frankly, to be kind of perfectly blunt with you, in order to be successful with microservices in general and microservices at scale, your shop has to be pretty sophisticated. You will not be able to do it without end-to-end testing and like full coverage. You will not be able to do it without without having a really solid CI/CD pipeline. Your DevOps has to be top-notch. Your practices have to be at par. You will not be able to just kind of wing it from like click the deploy from your laptop and be done with it. No, it will have to be a process. It will have to, you have to go through pretty serious engineering discipline. But if you're able to do that, if you maybe start with creating CI/CD pipeline, you create your hello world microservice. It does virtually nothing. I would say start with creating your CI/CD pipeline. Start with creating your test suite and make sure that you can test everything that starts with hello world. And you start doing this. You commit to your Git repo. It starts the series of steps that ends up somewhere in automated steps end up somewhere in staging environment, and then there is a human intervention there. You click the button, it goes to production. Or something even more sophisticated where you do use, for example, App Mesh for automated traffic shifting, where you introduce a new version of your application, you start flowing some traffic to it automatically, and you automatically monitor the results, you monitor the logs, and if there is no 500s, if there are no 400s, you start gradually shifting more and more traffic to it, and as you keep monitoring automatically your outcomes, making sure there are no problems, you shift more and more traffic to the new version, and you terminate the old version at that point. So that way you can achieve the full automation of your setup. Start with that. Start with your DevOps and your site reliability engineering discipline. Then implement your strangler pattern. I personally think that the developers part of this entire journey is easier than overall department level transition that needs to occur if it's not there yet. So it probably will need to start with your CTO, your enterprise architects, your SREs, your DevOps, and if all is there, your job as a developer, although not trivial, is not going to be super difficult. Thank you.
So for those who might be interested in your talk on the 21st, do you want to give them a brief overview of what that's going to look like? And
yeah, sure, of course. I will talk about. I think is that the Kubernetes talk?
Yes.
Is it called something like everything you wanted to know about Kubernetes but were afraid to ask?
I believe so, yes.
Okay, so that silly name is really dear to my heart because that is effectively, it will be a pretty condensed introduction to Kubernetes. But if you stick with me through that hour of pretty packed material, even if you're exhausted by the end, I promise you, but next time you read something about Kubernetes, it will pop in your mind as, oh, I know what that is. Oh, this is familiar. So when I started learning Kubernetes, it was a pretty painful process. And it took amount of time that I think I kind of regret. It should not have taken that much. So I will give you the Reader's Digest of the like some physicists, like theoretical minimum of what you need to get successful with Kubernetes quickly. So that will be what it is.
Great. I look forward to it. So if we don't have any more questions, we'll go ahead and wrap up.
I was just one with this app mesh. This is the traffic shaping, monitoring, and all that stuff. the auto scaling, scale up, scale down, that would be handled by either Kubernetes scaling or your ECS scaling, that type of thing. And then your mesh redirects traffic and knows about additional pods, or does it provide another layer of auto scaling?
So you're right. The scaling will have to be done through the underlying mechanism. So it would be scaled through. So the scaling of your compute will be done through your Kubernetes, your ECS, because it effectively, the way it works is if it runs up against the ceiling of your instance CPU capacity, it means you need another instance. So instance level scaling will be done by your compute. Here, what will happen is if you don't need to scale, effectively, you will not have to cheat in order to achieve traffic shifting. You will not have to scale your instances or your pods to achieve the traffic shifting. Traffic shifting is one of the main features, and probably the first thing that people do is traffic shifting. The canaries, the blue-green deployments, because it's really easy to do, and you have the standard thing that this virtual router that does it. Of course, if you're paying attention, you will realize that you get kind of like a load balancer situation here, and that load balancer is a client load balancer because again, there are no virtual things in between. It's your client calling the service or your ingress a gateway envoy calling you, and that's all there is to it. So if you have two routes going to two different places, it means that the caller will have to call one and then another. So this pseudo-random or weighted traffic shifting will be implemented on the client. So that's one of the things to keep in mind, but it's actually a feature. So that's how it works. Hopefully it was at least somewhat applicable to your question.
No, perfect. Thank you.
All right. So are we ahead of time?
Yes, yes, we are.
Oh, I cannot believe this. Usually I run well over. So I was slashing and burning my presentation today to fit.
You did great. You played with plenty of time for questions, and it worked out really well. So
I think this is my first. I think usually there is absolutely zero time for questions. Hardly any, even not even time for me to cut and paste the feedback link in the chat. So I'm happy how it has worked out. And but really, where I leave you here today is with the homework. I highly encourage you to click that YouTube link, go through it, and leave me a nasty comment, and that it's just too packed with or whatever. But the good thing about YouTube videos, you can rewind and watch and listen again. And by the way, in the another Easter egg in that YouTube video is if you expand the description, there are also 4 links to open source resources that you may find useful. For example, if you go to AWS website and see how to deploy, for example, AWS load balancer ingress controller, it's a set of steps that you need to copy and paste, copy and paste, copy, paste, run, copy, paste, run, copy, paste, run. Instead of doing that, I created a PowerShell script. And PowerShell, by the way, of you who are on Linux or Macs, is cross-platform. Installing PowerShell these days is like installing Python or I don't know, a Node. It's fully cross-platform, so you can run it anywhere. And that script should simplify this quite a few processes. Also, another important thing I think is like the best of what I have so far is if you happen to be a Windows.NET developer, I have created a Helm chart for deploying containerized web applications to EKS with App Mesh. So it's App Mesh aware, and the values file of the Helm chart allows you to specify whether or not you want to incorporate App Mesh and whether to use it or not to use it.
Well, great. So as you said, I will post the links that you put in the chats to the meetup page, so everybody's got them. If you, for whatever reason, can't get them now, as we discussed, the slide deck will be up there as well. And I will I'll post a link to the meetup for AWS Atlanta, so you can sign up for his session if you want to see that at the end of the month. So
thank you very much. Appreciate it.
Yeah.
Mark,
So,
thank you very much for hosting this. This is really great.
Oh yeah. Thanks for joining us, and thanks for talking tonight. This
Anytime.
Yeah, I look forward to trying out your link there. That's and contrary to what Vlad says, leave him a nice comment instead of a nasty comment. He deserves it.
Thank you very much. Thank you.
Yes, thank you. And just to wrap up here, we will be picking back up next month on May 6th to discuss authentication with Eric Bowman's. So hope you all will join us then. The meetup event page is up, so please sign up. And outside of that, thank you all for joining us tonight, and hope you got as much out of this as I did. And we look forward to seeing you next month. So have a great weekend, and see you then.
Thank you, everyone.
Thanks all.
Take care. Bye-bye.
Bye.